Welcome to week 9. In this lecture, we'll be looking at a couple of different topics. We'll look at statistical data that you all probably learned about in your statistics course in undergraduate. We'll also do a quick review to look at the interpretation of diagnostic tests, and then we'll finish with analyzing power and sample size in studies. In this lecture, we'll review how to calculate measures of central tendency, including mean, median, and mode, and review measures of dispersion, like standard deviation. You should be able to classify biologic variables into categories. You should also be able to evaluate the size of the impact of effect size, alpha and beta on both sample size and power. And you should also be able to calculate the sensitivity, specificity, and predictive values of diagnostic tests given appropriate 2x2 tables. The first part of this lecture is going to focus on basic statistics, and unfortunately the clinical dilemma is kind of lame. You're a pharmacy student who had to take statistics in an undergraduate coursework to gain admission to pharmacy school. You now find yourself in a drug literature interpretation course, finding that you've forgotten the vast majority of what you've learned about basic statistics. You'll need to these skills in order to develop into a critical thinker and literature interpreter. So let's review some basic concepts. In this first section, we'll look at measures of central tendency, basic measures of dispersion, and how to classify variables in studies. Let's start with some basic definitions. Statistics, which can be broadly defined as the science of learning from data and of measuring, controlling, and communicating uncertainty, comes in two basic varieties in the medical literature: descriptive and inferential. Descriptive statistics are used to summarize, organize, and present information in statistical format. Common uses in medical studies that we've already looked at would be describing baseline information between study groups. Descriptive statistics include measures of central tendency like mean, median, and mode, and dispersion. Inferential statistics, on the other hand, are used to analyze and interpret relationships. So you can think of these as the tests that we use to assess associations between variables and outcomes. Common uses of inferential statistics would be hypothesis testing, assessing differences between groups, and they include the statistical tests like t-tests, Mann-Whitney U-test, ANOVA tests, which we'll look at in detail next week. If you think back to how we've been categorizing studies, we typically classify them as descriptive or analytical. Descriptive studies are studies which only use descriptive statistics, whereas analytical studies use both descriptive statistics and inferential statistics. When we've been performing statistics or statistical analyses, we're looking at data in the form of variables. And there's a couple different ways to classify variables: quantitative and qualitative. In the medical literature, quantitative information and quantitative studies are far more common. However, qualitative data is very useful in certain niche situations. Quantitative variables are simply data that are collected as numerical or countable information, so data that deals in numbers. You can think of things like age or weight or blood pressure. These variables are the most common type of variable that you'll find in medication studies. However, there is a different class of variable called qualitative variables, which are data that are expressed not in numbers but in words. These would include interviews with patients or providers, written observations, notes from a medical chart. And although they're less common in medication studies, they are useful in certain situations. For example, say that you find a study that socioeconomically disadvantaged people have worse adherence to their medications than more wealthy patients. With quantitative data, you can show that their on-time medication refills are far lower and that this is significantly different. So it tells you that there's a statistically significant difference between groups, but what it doesn't tell you is why that is the case. If you want to know what prevents a patient from filling medications on time, you may want to conduct an interview and thereby generate qualitative data to get the patient's perspective, which can be extremely valuable in this case in trying to circumvent that issue. We can break down quantitative variables further. Quantitative variables can be discrete or continuous. Discrete variables are variables which have only a few possible values, and they're often called counts. For example, discrete variables could be things like biological sex, male or female. There's only two possible options. mortality, you're either dead or you're alive. And there are a lot of other variables used in the medical literature with yes or no answers, such as was a patient readmitted at the hospital within 30 days of discharge, yes or no. Most discrete variables are counted. Discrete variables can also come in the form of survey responses on a scale of 1 to 5. How do you agree with this? How much do you agree with this statement? So you only have 5 discrete values, which that variable can be for each patient. Continuous variables, on the other hand, are variables which can take on an infinite number of values in a given range. Examples of these would be height, body temperature, and weight. So they can be any value, not just certain fixed heights, temperatures, or weights. Most continuous variables, instead of being counted, are measured, and really the main difference between a discrete variable and continuous variable is how accurate you can make that measurement. For continuous variables, for height, you can say someone is 6 feet tall, or you can say they're 72 inches, or depending on how accurate your instrument is, you can say that they are 62.578 inches. You can get more and more detailed because it's on a continuous spectrum. Finally, we'll look at one last way of classifying variables, and that is to group them into distinct categories that include nominal, ordinal, interval, and ratio. The classification of variables is important because it depends on how we calculate things like power, sample size, and what statistical tests we can run on the individual variables, because the variables take on different statistical distributions. The first variable type that we'll look at are nominal variables. Nominal variables are data that can be placed into defined categories without any implied order, and sometimes these are called categorical variables or dichotomous variables. They usually have very few categories and there's no implied order. For example, biological sex is either male or female. There's no order here. Mortality is dead or alive. We can't rank these in any sort of meaningful order. So when we're using math to describe these variables, we can simply only count them individually and describe them as frequencies. For instance, if we say there were 55 males in the study and 45 females, we could say 55% of the study population was male. We can't do more complex math because it's not meaningful on these types of variables. Even if we coded all males as 1 and all females as 2, and we found out that the mean sex of our study was 1.75, that doesn't make any sense to anyone. It's a meaningless variable. The next type of variable would be ordinal variables, which are data that are categorized into narrowly defined categories like nominal data, but the categories have an implied order. A common example of this would be Likert type scales, like a pain scale. So on a scale of 1 to 10, how severe is your pain? For mathematic operations, we can be a little bit more complex. Because we can rank the individual data points, we can get a middle value or a median. We can grab percentiles, so the 25th percentile value that is, or the 75th percentile was that. However, we can't do addition or multiplication as the units of measurement are not defined and that they're subjective. When I rate that my pain is a 7, you might rate that same amount of pain as 5. So we can't do more complex math beyond just ranking them and describing them. The third variable type are interval data or interval variables. Interval variables are continuous data that are ranked in an order with meaningful differences between numbers, but they lack a defined and meaningful 0 point. For example, since this is a continuous variable, we can look at something like temperature on a Fahrenheit or Celsius scale. We can do addition and subtraction math operations because we're using a scale that has a meaningful difference between numbers, and we have instruments that can measure these numbers accurately. However, the 0 point for Fahrenheit and 0 point for Celsius aren't meaningful in any sort of natural or biological way. There's still different temperatures below 0, so -10 is a feasible temperature. So 0 is not an absolute in this situation. The other type of continuous data that we'll talk about are ratio data. And this is very similar to interval data. It's continuous data which are ranked in order with meaningful differences between numbers. However, there is a meaningful 0 point. For example, blood pressure is an objective continuous variable that we can measure. However, 0 blood pressure is meaningful. This means there's a complete absence of blood pressure. Height has a meaningful 0 point. 0 height means essentially that it's non-existent. 0 weight is meaningful. So blood pressure, age, height, and weight are all ratio data. In ratio data, all math operations are feasible, so we can even use multiplication and division because that 0 endpoint is in play as well. Let's briefly recap what we talked about in terms of variable classifications. The left-handmost column on this chart is the level of measurement, so nominal, ordinal, interval, and ratio data. Nominal data and ordinal data are both discrete. There's a limited number of values that those two variables can take. An example of nominal data would be male or female, race, whether or not a patient is insured. So these are different categories which can't be ranked. Mathematical operations we can do are simply counting the different data points for each individual bucket and then describing them as a frequency. For ordinal data, again, we're limited in the sheer number of options or values that a data point can take, but they have an implicit order. So Likert type questions. How much do you agree, 1 through 5? Pain scores. How much pain are you in, 1 through 10? For these data points, we can count them, but we can also arrange them in a meaningful order, and therefore we can find the middle value, the median, or different percentile ranks along the spectrum. Interval data and ratio data are both continuous, so there are theoretically infinite number of data points in which these variables can take within their range. The example of interval data we talked about is body temperature and Celsius or Fahrenheit. There is an infinite number of values this can take, and we can measure it. However, the 0 point is not meaningful, so we can use the same mathematical operations as ordinal data. However, we can also do addition, subtraction, we can take the mean value, and we can take standard deviations. Ratio data is similar to interval data, except the 0 point is meaningful. These are things like age, weight, height, and income. We can do essentially the same mathematical operations as interval data. Now that we have our variable classification set up, let's talk about how we can classify these variables by their measures of central tendency. Measures of central tendency are used to provide information about the center or typical value of a set of numbers, and there's 3 major ways to estimate this in statistical studies. The one that we're probably most familiar with is mean, which is the average of a data set. To come to this number, we add up all individual values and then divide by the total number of observations. This really only should be used with continuous data and what is called parametric distributions, which means normally distributed values. We'll talk a little bit more about that on the next slide. The median is the value in the middle of the data set. To calculate a median, you arrange the data in ascending or descending order and then report the value that lies in the direct center. If there are 2 values in the direct center, you take the average of those 2 values. Medians are typically used for ordinal data, so when we have that ranked order or data sets in which there are obvious outliers, meaning non-parametric data, meaning data that's not normally distributed. Again, we'll talk about this briefly in the next slide. Finally, there's mode, which is simply the most commonly occurring value in a data set, and we can use the mode for nominal data. So which values are the most frequent? Male or female? Did most patients live or die? Those are the 3 measures of central tendency that we will go over in this course. There's one aspect of central tendency that needs to be discussed a little bit further, and this is the fact that medians are resistant to outlying values, whereas means tend not to be. So if we look at this through an example, say that you're collecting data on 7 people and you want to know the central value. In a parametric or normally distributed or bell-shaped data set, the mean is 68 inches. However, if one of those 7 people was replaced by an NBA star, Yao Ming, who has abnormally high height, so a positive outlier value, the mean would go up to 71 inches, but the median would remain 69 inches. Although this isn't a very big deal for height, in non-biologic variables like income, the mean can shoot up far, far greater than the median, and therefore the 2 values will be very different. But the median will tend to be a more realistic value because it's the middle value, and it's not impacted by these very high or very low outlying values. So highly outlying values and non-parametric data sets cause mean values to become more deviant and less representative of the underlying data. Let's look at this little figure at the bottom. The normal distribution is a parametric distribution, and it's shown in the middle figure B. And the mean, median, and mode are all approximately equal. If the data is negatively skewed, as in figure A, meaning you have very low values that are abnormal, your mean gets pushed farther to the left, and the median and mode tend to stay more normal. But the median is the most accurate value overall. And converse, if in figure C it's positively skewed, again, the mean tends to be pulled further away from the middle, and we'd want to use the median again in those situations. That was measures of central tendency. Now we need to look at measures of dispersion, which are used to describe how data are spread and provide most of our information about the variability in the distribution of observations. The central value is our most commonly occurring value, which is said to represent the data set maybe most accurately. The measures of dispersion tell us how far other observations are from that middle value and tell us a little bit about the precision of the estimate. The mean estimate is the central value, but then there are values that are far, far away from that mean, and it might mean that our sample is not very precise. So for measures of dispersion, range is probably the most simple to comprehend. It's just the maximum value subtracted from the minimum value. The interquartile range is used for ordinal data. It's typically the 25th percentile value through the 75th percentile value, or the middle 50% of values. Another way to think of that would be the median minus 25%, all the way through the median plus 25%. That's again for ordinal data usually. Then we have variance and standard deviation, which estimate the variability of individual observations around the sample mean used for continuous data. If we look at the equation for variance, it looks really complicated, but what it essentially says is that you subtract each individual observation from the mean, so then you're essentially assessing how far away each individual observation is away from that mean. Then you square that number so that all your values are positive, and then you take the sum, so you're adding up how deviant all those different values are, and then you divide it by the total number of observations minus 1. That's variance. Standard deviation is simply the square root of the variance, and it's interpreted in the same way, although it's a little bit more commonly reported because the units match those of the mean. To look at measures of dispersion, and in particular standard deviation, we can look at a parametric or bell-shaped curve. On this curve, the mean value is at 0. One standard deviation on each side of the mean contains about 68.2% of that data, and it kind of dwindles down from there. So 2 standard deviations on each side contain more data, and 3 standard deviations on each side contain about 99.8% of the data. Standard deviations are essentially telling us how far removed individual data points are from the mean. We'll take a more in-depth look at statistical distributions next week, but for now, this concludes video 1. In preparation for the quiz, you should be able to recognize the mean, median, and mode for a set of data. You do not need to know how to calculate variance or standard deviation.